So I'll be touching upon facets of system operation and planning from the perspective of challenges that we face when there is a lot of integration happening in the grid. I believe some or most of you would be very well aware of the situation that significant renewable there has been a significant push on renewable penetration in the grid, and the government of India is aggressive on putting in as much renewable penetration, renewable generation as possible, focusing on two technologies primarily. One is on solar generation, the other one is on wind power plants. These things obviously come through a variety of mechanisms. I'll take you through this. What is the Indian power structure as of now? Key legislation policies. What is the capacity mix? Slightly dated, but I'll touch upon these few things and what is evolving within this segment. Challenges that we face on RE growth and the impact, primarily that is the focus. So our main focus would be on the last part of this these slides, which are on system planning, system operation, and for future markets. So this is quite generic. We all understand growing economy. We all require the size of the grid is quite large. It is one of the largest integrated grid in the world. Per capita consumption, electricity consumption is low at present, but it is increasing and it will increase to a significant level over the next couple of years as we see more and more electrification happening in the system, in the overall energy supply system. India, there are challenges, there are opportunities as well. Challenges in terms that India is facing on the energy supply side. We are dependent on international supplies for our oil and gas supplies, partly for coal as well. However, the good part is we have got significant opportunities for producing renewable generation using solar and wind, offshore, onshore. The generation mix is also evolving towards nuclear generation over the last year or two to ensure that there is energy security in the system. On the renewable energy targets, there are INDC targets, that is intended nationally determined contributions, INDC targets, are to attain 40% of the total capacity generation, total electricity generation from non-fossil fuel sources by 2030. We are on that path and we hope we'll be there very soon prior to 2030. This was a target 75 gigawatt of renewables in 2022. We have surpassed that well ahead of time. The challenges that we see are because of the large size and because of the renewable penetration that we are pushing in, large requirement in the grid. There is a significant requirement to invest into the grid. Now the question is how to do it optimally. There are various ways. Optimally, we could do it through appropriate market interventions. We could do it through appropriate investments into the system and through regulatory changes in the grid. So what we look forward to is just a quick glimpse of how the sector is picked up. On the policy front, who all are the players? The central government is aggressively doing, the Ministry of Power and Central Electricity Authority, they handle the policy front, policy and planning as well. Apart from this, Niti Aayog is also a part and parcel of the attached to the central government. State governments as such do planning, a bit of policy making, but significant planning is there. On the regulation side, we have got regulatory bodies at the central level, CRC, and state levels, SCRCs. On the generation side, we have got central generating stations like NTPC, NHPC, NPCIL, etc. There are mega power plants at the state levels, also GenCos and independent power producers. A lot of those are there. Transmission Power Grid Corporation of India Limited is the transmission licensee at the central level. At the state level, they've got their own state transmission licenses. System operation is presently being handled by POSOCO or Grid India Limited, having entities like National Load Dispatch Center and Regional Load Dispatch Center under its domain. At the state level, we have got the state load dispatch centers, which do the load dispatch and which manage the operations, which manage the control rooms at the for load dispatch. On the distribution side, also presently there are distribution licenses at the state level, central level. Central government does not interfere much into the spectrum of distribution licensee. Trading licenses are there, those who participate in the market, and appellate tribunal are there at the central level for appellate, not at the state level as of now. Having said that, this situation is evolving. We are, I think, over this month, you'll see a lot of changes happening in this segment on trading, where peer-to-peer energy trading is being introduced in the Indian market, allowing people from one state like Delhi to buy and sell electricity from other states on a peer-to-peer basis, like UP or other states, wherever it is getting feasible over the next couple of months. So this segment is seeing active, a lot of activities happening, trading. Similarly, we'll see all these things are being supported by appropriate legislation, appropriate policies. There has, I hope I'm audible.
Yes, sir.
Okay. Let me know in case if I'm not audible, just let me know. At times I feel the internet connection may not be so strong. This is being supported by key legislations like Electricity Act, electricity policies, 2005. Now we have got a renewed policy, electricity policy as well. Tariff policy, it was initially promulgated in 2006. Thereafter, there has been changes in that as well. Electricity Amendment Bill 2020, and it has significantly evolved, or two amendments have come up after that. That is essentially leading. What we are looking forward to is it is likely that we'll be having distribution licenses being separated out from the content provider, that is retailers, are likely to come up in the system over the next phase of deregulation that we see in the industry. Capacity mixes slightly dated, but I think this is, if we go by the percentage, more or less it remains similar. RE penetration is increasing. This was slightly dated because we could not get complete details of the updated numbers at some point of time. However, I'll skip this. These are slightly dated numbers. Coming to the point, what are the challenges with RE growth? One of the key challenges that we see with renewable penetration is the relatively high investment costs involved. Obviously, when you're putting up solar generation plants, you need land. When you're putting up wind turbines, they are costly. Apart from those, one of the challenge is the present infrastructure does not have the capacity to evacuate that power when it is getting concentrated in certain areas like Western Rajasthan. Another challenge is that these sources are intermittent, they are unreliable for secure power supply. Grid operation has to be more focused now. These are issues of major concerns because monitoring and control requires a lot of effort from the present scheme of things, in which there are large number of distributed generators in the system, so monitoring and control has to be enhanced. The challenges that we see when we have got variable renewable energy being supplied into the grid, these are non-synchronous generation systems, which requires us to focus on appropriate frequency and voltage responses in the system. Essentially, present mechanisms of frequency and voltage regulation, voltage response, were traditionally designed for thermal power plants, which were dominant in the grid. Now, these renewable generations, they are non-synchronous in nature. So they essentially require adequate support in terms of frequency and voltage response, which they are not able to get from renewable power plants to that extent, which was relatively easy for in the case of conventional power plants. Locational challenges, location constrained, and they are distributed. So that again, they are constrained in certain locations like Western Rajasthan, in Jammu Kashmir, Gujarat, Tamil Nadu, Andhra Pradesh. These states, they are concentrated. So that leads to requirement for more network infrastructure and voltage management as well, because this is when the generation comes up and goes off, it happens at a very fast rate, and those ramping requirements push the system operator to manage the voltage in a very aggressive way. Other big challenges with the system are uncertainty. The system remains uncertain because of the uncertain nature of the generation. Though predicting solar generation is relatively easy, but predicting wind generation is relatively difficult. This uncertainty requires, what essentially it would require is that the grid should have flexibility to handle that uncertainty, which presently was limited because thermal power plants were operating at a higher technical minimum of somewhere around 65, 75. The government is trying to push down that technical minimum so that those power plants can provide more flexibility. However, even that is not sufficient, and the push for demand response, as I discussed earlier, would be there in the system. Variability is another challenge. The generation from the solar power plant that comes up in the morning, it goes down the evening. In the evening, the variability that it creates in the grid in terms of ramping up in the morning, ramping down in the evening, that essentially pushes us to bring in other type of generators uh, down in the morning when the solar generation is coming up, and to bring up the rest of the generation at a very fast pace at around 4 o'clock in the afternoon when the solar generation starts going down. 3 to 4 o'clock, you have to bring in every day. This is a problem in which other power plants, their generation has to be ramped up at around 4 o'clock till 10, 11 p.m. in the night. And again in the morning, before the sun comes in, whatever is the demand, that has to be fulfilled by the conventional power plants. So twice a day, the other generators other than solar generators have to be pushed in. Similar type of challenges come up with the wind as well, because wind is typically coming, or I would not say typically coming, but it is significantly coming up during night hours, which pushes the thermal power plants to their technical minimum, leading to a situation where the cost of these power plants are not even able to recover the cost of generation, and the cost of electricity in the grid goes down to at times to 50 paisa per unit or even less than that. These variability challenges, they require what they require from system operator or the system planner is to bring in mechanisms for flexibility and bring in firm capacity into the system so that variable capacities do not challenge system operation. Same type of challenges, or I would say challenges with a longer time frame, they are there in the planning stages as well. For those non-synchronous generation, you have to do technical network studies. What is the quantum of inertia that they would be able to provide? What is the network capacity that you would require to evacuate all that generation that is coming up at certain times of the day, not at all times of the day? What type of storage you would require in the grid, just to ensure that whenever there are peak generation available and network does not have capacity, how do you handle that excess generation? Either you store it through batteries or you can try to convert it into hydrogen. Those type of challenges are to be focused on the planning side. Geospatial planning and technical network studies, obviously, network planning forms an integral part of this. Evolving from uncertainty and requirement for flexibility, that essentially requires us to focus more on dispatch simulations and to understand what type of oscillations, what type of system operation challenges would be faced, and based upon those, we need to make appropriate investments into the system in terms of network capacities, in terms of other power electronic fact devices, which can help to control the power flow in the grid and keep it stabilized. Variability challenges obviously have to be looked into from the perspective of generation expansion planning. So we plan our generation in such a way that the variability, not only the generation, the variability of renewables can be mitigated, the variability of the uncertainty of demand can be handled by putting in appropriate firm capacities in the system. So there are three facets that we'll be touching upon quickly in this session. One is on long-term system planning, the other one is on system operation, and third one is on transition towards future markets. How do we see all these issues? From system operation perspective, three issues that are becoming important are important as of now and are likely to be more important in the future as well. One is that of inertia and primary frequency response support in the grid. The other challenge is related to operational flexibility, and yet another challenge is related to operational reserves. These are the fundamental challenges that the grid is facing. And to ensure that we mitigate, some of the challenges have become significantly large, like operating reserves have become significantly large, operational flexibility. These two challenges have obviously become significantly large in the grid as of now, leading thereby to focus of the industry on resource adequacy studies over the last 2-3 years. So this is a segment which has drawn significant attraction in the industry. Inertia and primary frequency response, this is yet to come up as a bigger challenge because um, the minimum level of operation of thermal power plants is still decent enough, and the grid is not facing challenges during those hours when the demand is there. What is happening is during the daytime when the peak demand is coming up, the solar generation is able to support it, so that compensates to a significant extent. So the challenges of inertial support are relatively low during the day hours. However, the challenges are coming up during the evening hours when, but then thermal power plants and hydropower plants are able to support the grid. So presently the mix is decent. However, the challenge is likely to become significant when we see maybe down the line 2, 3, 5 years down the line where RE penetration would increase. Some of the old thermal power plants may be taken out of service. That is a situation, and added on to that, the wind generation also, it is coming up in a significant way at certain places in offshore, onshore. That is a likely situation where inertial support may not be sufficient for secure operation of the grid. You see, this is a reflection of what the capacities of solar and wind capacity factors, which indicates what is the quantum, what is the generation that is available in different cells. When we bifurcate the country into cells of 110 kilometer by 110 kilometer, we see what is the concentration of solar generation capacities available. This is not the generation that is exactly presently there in the system. This is a reflection of what are the capacities available of solar generation, what are the capacities available of wind generation in the grid. So if we see, solar generation is significantly concentrated in the northern parts, in the western part of the country. These are the two areas where solar generation is concentrated. Wind generation is concentrated on the western part of the country, Rajasthan, Gujarat, Maharashtra, and the southern states associated with those. So these are the two areas where renewable generation is concentrated. The capacities are concentrated, where they have got the potential to generate solar and wind energy. It is not exactly a reflection of what is the generation that is happening. So one of the planning perspective that we need to do is to have an integrated resource planning in the system. Integrated resource planning in the system would require appropriate load forecasting, short-term and long-term framework, identify what are the goals that you need to fulfill, what are the goals of power demand, what are the goals of ramping requirements, what existing resources do you have got, what would be the new resources, if we subtract what is the capacities available, what are the existing resources, what would be the new resources that you need in terms of supply, in terms of demand, in terms of transmission distribution, and thereafter broadly identifying what should be the suitable resource mix that you would require to have a stable and a secure system operation and planning. For that, we do a sensitivity analysis and identify which type of generation, which generation mix, which resource mix would be able to handle the system operation planning in a proper way. The impact that we see presently on system operation planning, when we have focused on identifying what are the capacities available in the system, and we have been able to see on a very granular scale that this is based upon our research in terms of identification of what is the RE available in the system. So this capacities, they indicate what are the areas. Presently, what was happening was we were focusing more on a broader scale, identifying what is the capacities in Rajasthan, what are the capacities in individual states. However, when we start identifying the capacities in smaller areas of 110 kilometers each, they help us to understand what type of network integration, network capacity investment is required when we are trying to transfer power from one cell to another cell, rather than from Rajasthan to UP, Rajasthan to Delhi, or Rajasthan to Punjab. We need to focus upon what are the network capacities that we would require if we are trying to transfer power from one geographical area to another geographical area. So this is the type of research that we have done, and this helps us to estimate the RE potential in each segment very clearly. And this essentially helps us to understand what would be the required capacity investment and what are the required flexibilities that we would require to operate the system. From a long-term planning perspective, the challenges that we see presently, one of the broader problem that we face is when in a very generalist mode, when people say that these are the capacities of renewable generation that are coming up in the grid, we typically say the renewable generation is coming up 100 gigawatt, 150 gigawatt, 200 gigawatt. These are the terms that we generally use. However, when we use these terms, we are not very clear on what is the time scale, at which this generation is coming, what is the spatial distribution where all that generation is coming up in the grid. Until and unless we have a clarity of what is the time scale in which the generation is coming up, at what hours it is coming up and what hours it is not available, planning in the system becomes a challenge. Until and unless we know the spatial resolution, where exactly this generation is coming up, we would not be able to make appropriate planning decisions in the system. This requires, essentially it requires more understanding of geospatial capacities in the system so that appropriate geospatial planning of the system can be done. Because without it, it would be difficult to understand what are the network capacities, what are the generation capacities that would be required in each geographical area, depending upon what is the demand that exists in certain areas and what is the generation that exists in those areas. So site-specific transmission capacities to identify those and to represent those, that is required on long-term energy system planning models. That is required for geospatial planning of these models. And further, understanding this, we also need to identify what would be the production cost models in the system. These help to minimize the operational cost of generation in the system. Thereafter, we also need to figure out what should be the grid models that we are using so that our dispatch and operational decisions are appropriate. With whatever generation is capacities are available in those cells, we need to adopt appropriate grid models as well, such that we identify what type of network, what is the capacity of network that would be required, whether there would be a congestion in the system, whether we require a load dispatch, redispatch or not. Those type of system studies have to be done. Thereon, once we understand the operational decisions, once we make the operational decisions in time frames of hours to days, we also need to understand the dynamic grid models in time frames of milliseconds to minutes, so that steady operation of the grid can be ensured. Feedback from all these models, from geospatial planning, from production cost, from the grid models and dynamic grid models, static as well as dynamic grid models, all these models input has to go into long-term energy system planning model, so that adequate capacity from all these perspectives and optimal capacities from all these perspectives is available to plan the system. So not only do we need to understand what is the location, what is the time frame in which the generation comes, we also need to understand what are the costs involved so that the overall cost of generation is minimized, overall cost of producing as well as supplying electricity is minimized. We also need to focus upon the grid models so that the overall investment in the grid, both in terms of the capacities as well as in terms of maintaining grid stability, are there. And all these are integral part of long-term energy system model, which have low details. These models would, as you go down the timeline, these models would have minute details possible. However, their scope is very narrow. So when we talk about dynamic grid models, we usually talk about very small time frame system operational model. Or oscillation is one of the challenges. Primary frequency response is one of the challenges in dynamic grid models. In static grid models, we talk about unit commitment and optimal power flow. Production cost model also, we focus on those areas of cost modeling. Geospatial planning models are at a higher scale. What we talk about in planning framework, and all these planning framework from electricity grid system perspective, and all these inputs go into the perspective of long-term energy system modeling, which has got low detail but wider scope in itself. Coming down to specific challenges, we have challenges of one of the challenges that we are facing in the grid is that of primary frequency response, in which because of because of the own inertia of the system, what we quantify frequency response characteristics, megawatt generation lost or load lost divided by the change in frequency. So if F naught is the standard frequency at which the grid is operating, and there is a sudden disturbance that occurs at point A, so this is the standard 50 Hertz frequency. As soon as there is a disturbance in the grid, maybe a loss of generation, certain megawatt has been lost, which leads the system frequency to go down from its standard value to the lowest nadir value of F nadir. This indicates the inertial weakness in the grid. Thereafter, the time that is required to recover that grid from the lowest point to a safe zone and then to a standard value, it would depend upon what are the primary frequency response characteristics of the grid what are the secondary frequency response characteristics of the grid, and what are the tertiary frequency response characteristics of the grid. These obviously depend upon, primary frequency response depends upon the characteristics of the grid. Secondary frequency response would depend upon what are the response mechanisms, and also the tertiary frequency response systems. The response mechanisms that have been installed in the grid in terms of automatic generation control and optimal power flow, and if there are any other market mechanisms to respond to these tertiary frequency response mechanisms. Primary frequency response mechanisms traditionally have been dependent upon the grid characteristics in terms of inertia. So that is something, is a technical solution that we primarily need to focus upon. So just linking this time graph with these, inertial response is a response of the grid that is usually provided in time frame of 0 to 5 seconds with an objective to balance the power, with an objective to maintain the transient frequency dip, to minimize this transient frequency dip. So if you see this dip is what is to be minimized. To minimize this dip, you essentially require a strong inertial response in the grid, so that whatever is the loss generation happening, the dip is minimized to the dip is minimized to the extent possible, so that it does not get out of the standard frequency range of the protection system. Let's say if the frequency range is defined as 49.95 to 50.02, in any case, the frequency should not go below that level for a very long period of time, else the relays would get triggered, the circuit breakers would start operating to isolate the grid. So the role of inertial response is to provide support during that time. Primary control, that is the automatic generation control, even before that, the governor control that operates in a time frame of 1 to 20 seconds. The aim is again for balancing the power and recovering, providing recovery support for transient frequency. Automatic generation control, which works as a part of secondary control mechanism, it works in a time frame of 4 seconds to 3 minutes, approximately in this range. The aim is again for power balancing and maintaining steady frequency. It is done through regulation. That is, essentially, it injects, let's say, in terms of thermal power plants, it would inject more fuel into the power plant so that the generation of that power plant increases. So that is something that depends upon the generator's characteristics to respond to those ramping requirements at a fast pace. That is what comes under the framework of regulation. Tertiary control, which comes from a longer term time frame of 5 minutes to 50 minutes, that can be dependent upon power balance and economic dispatch. So essentially, economic load dispatch, through economic load dispatch, we could do tertiary control, which would essentially ensure that load following is done appropriately and appropriate reserves are maintained in the system. I'll not get into this technical diagram as of now. This information, this is quite a comprehensive reflection of the reserves that are required in the system, the balancing requirement, and the frequency reflections in the grid. So this is again a similar reflection. In the time frame, we primarily require inertial support during the first few seconds. Primary frequency response, the same things are plotted here as well, and these indicate the capacities. If the height is more, obviously the peak requirement would be high. If the area is more, that indicates a wider energy requirement. And this is something that time indicates for in what time frame it is required. So these are activities which are required in a shorter term time frame of milliseconds, milliseconds, minutes to hours, and day and longer time frame. Indicative responses and attributes are: inertial response is required in first few seconds. Primary frequency response is required in maybe up to 5 minutes. Secondary frequency response up to 15 minutes. Fast tertiary response up to 30 minutes. Slow tertiary response up to 60 minutes. Thereafter, generation rescheduling, they work in the time frame of 60 minutes and more. Unit commitment works in the time frame of hours and day ahead. Quantum wise, the quantum required is in capacities, megawatt per hertz is significantly high. It is approximately 10,000 megawatts per hertz. So the peak demand in this case is very high. As you see, in the primary frequency, the frequency response, it is up somewhere around 4,000, 1,000 megawatt. Low tertiary response is slightly higher because by that time, the grid has to respond. And rest of the generation demand obviously comes through, which comes through unit commitment and economic load dispatch. There are no capacities defined. It could be any large capacities, whatever is the balancing requirement in the system. The requirements in the system, inertial and primary frequency response, are essentially provided through local response mechanisms. They cannot be provided at the grid level because the time frame to respond is too large. Secondary and tertiary responses, obviously, they can be handled at the national load dispatch centers or the state load dispatch centers, and so on. When we see these balancing requirements, generation rescheduling, those also are done at the in the time frame, which is typically being handled by the load dispatch centers. Inertial and primary frequency response, they are essentially automatic in nature. The system has to respond automatically. They cannot be manual in nature. While as the time frame increases beyond 5 to 15 minutes, it becomes manual in operation. So humans can also intervene to provide all those responses in the system. They can operate the grid in such a way. However, inertial and primary and secondary frequency responses, they have to be automatic in nature. Again, the local responses are decentralized, while the responses happening through the load dispatch centers are significantly centralized. However, optimal power flow decisions, those could be again be decentralized because that is happening at the state load dispatch centers, and below that at power plants also, power plant level also. If any power plant has got 5, 6, 10 units, it can still do an optimal dispatch within its unit. So that can be decentralized to the extent possible. There are codes or orders which have to be followed. IEGC codes have to be followed. There are ancillary regulations that have to be followed in this segment. The services as such, these services which are automatic in nature, these are essentially mandated services. However, as you go on a longer term time frame, those services can be market based or regulation based, and they would have to be paid for. So if you are providing, if any generator or any utility is providing these services, it would be appropriately compensated for providing those services. While for providing inertial and primary frequency response, they would not be compensated to that extent, but they would be expected to provide those services on a standard regulatory form. These obviously, the initial services, the short-term services, they are regulated to a significant extent, while the longer term services, they can be regulated or they could be market driven, because market also would have the capacities to respond in time frames of 15 minutes, 30 minutes and beyond. Some of those services like inertial frequency response services, they are there in the system. Primary and secondary frequency response services are evolving, while economic load dispatch and slow tertiary and other unit commitment generation rescheduling services are obviously available in the system. This is a generic reflection of what is the state of affairs as of now. The challenges in this segment, the system operators are able to see, and that is essentially what is pushing capacity investments over the last 2-3 years on the nuclear generation side, one, Another investment that is happening is because of on the side of battery storage, that is to handle the challenges in this time frame, in the shorter term time frame. These are the two key changes that are happening in the industry as of now. However, in this time frame also there are economic decisions like security constraint economic dispatch that is presently evolving in different states, and it is likely to be adopted at the central level also. Presently, it is in the policy framework, national electricity policy also, it is there in that framework. As we move towards higher penetration into the system, the intermittency would increase, the higher rock requirement and lower frequency nadir the grid would be facing. So frequency response requirements would increase. There would be a declining share of conventional sources because thermal power plants, hydropower plants, their percentage would decrease as a part of percentage generation, which would obviously require to have increased system inertia and primary frequency response requirements in the system, which presently is declining over a period of time. So if there is inadequate inertia in the system, frequency events of frequency falling there would be more events when the frequency is falling, and under frequency load shedding would increase, leading to cascaded events and blackouts. So this is one of the key challenges that the grid is facing, which is likely to face in the upcoming years. Some of the possible solutions that we have identified that we feel could be and what are being adopted as of now, some of them can come from the demand side, some of them can come from the generation side. On the technical solutions that are available, one on the energy storage side, some on the RE-based side. Then there are solutions available on electric vehicles. Demand response could be in terms of load management, or it could be in terms of appropriate solar generation at the load side. This type of system challenges, if you see what these type of generation would bring into the system is, this is just to give you a reflection of the flexibility requirement in the grid, in which if you see the load in the grid is indicated by this purple dotted line, which indicates that the load is coming up. It is low during the early morning hour time till 4 a.m. Thereafter, it starts increasing, remains high during the daytime, and again ramps up during the evening hours at around 5 o'clock, 6 o'clock, 7 o'clock, or 8 o'clock because of the lighting load, and then goes down. The solar generation, if you see this dotted line, the solar generation that comes up in the grid at around 5 o'clock, ramps up from about 6 o'clock to 9 o'clock, remains stable during the day, and starts going down after 4 o'clock to 7 o'clock, it just goes down. So this indicates the solar generation in the system. Wind generation in the system is significantly intermittent. This is the graph of renewable wind generation. Eventually, if you see what is the net load requirement in the system, which is an indication of the load requirement that is to be fulfilled by conventional power plants other than solar and wind, other than renewable generation in this grid. So when you see that requirement, the net load requirement in the system remains low during the early morning hours, but because of solar generation coming up, or the demand coming up in the morning, the requirement increases in the morning hours. But as soon as the solar generation comes up at around 6 or 7 o'clock, the net load requirement in the grid would start going significantly down. The solar generation remains up. The net load requirement, that is the generation that we would be sourcing from conventional power plants, that would remain low during the day. As the solar generation goes down in the evening and the demand increases, the overall demand increases, the net load demand, because of the decreasing generation, solar generation, and increasing demand, the net load demand on the conventional power plants ramps up during the evening hours in a very big way. And after 8 o'clock, when the demand decreases, the net load over the system also decreases. So effectively, this black bold line indicates the requirement, the generation requirement that is to be fulfilled from conventional power plants. And this indicates these times at around 4 to 6, 7 a.m. and from 4 to 7 p.m. in the evening hours. These two time frames indicate the time when ramping up in the grid is required. And then there are times when 7 to 9 when it is ramping down. Again, from 7 to 11 it is ramping down. So these are the time frames in which there are ramping up and ramping down requirement in the grid, which essentially require flexible generation in the grid, either flexible generation or flexibility to be brought in from the demand side. Flexibility could be there in the shorter term time frame requirements for optimal scheduling solutions, or from a long term planning perspective, in which appropriate generation mix, appropriate demand response mechanisms have to be put in place to provide those resources for flexibility. There are, if we talk about some of the flexibility, type of flexibilities that we would require, they would be in terms of capacities, they would be in terms of ramping requirements, they would be in terms of one power capacity, another energy capacity, and in terms of the delay that would happen in providing those services. So if the response delay is low, we presume that there is significant flexibility. If the capacities in those generation is high, we presume that there is flexibility. If the ramping limits are large enough, the generator is able to provide fast ramping up, ramping down solutions. We presume that they've got good flexibility in the system. And same is the term of capacities, whether it is a 100 megawatt power plant, 200 megawatt power plant, they indicate a higher capacity indicates higher flexibility in the system. If there are no flexibility in the system, it would eventually lead to renewable curtailment, load curtailment, or ramp insufficiency, which are essentially measures of non-flexible grid. So the solutions that we focus on to improve the flexibility requirement in the grid is through, there are a variety of solutions. You see energy storage, sector coupling, improved operation, demand response, grid investment, and generation side flexibility. These are some of the options that we adopt to provide grid flexibility. On the energy storage side, we have got variety of pumped storage, flywheel, and other storage mechanisms. On the sector coupling side, we could bring in the flexibility by integrating more electric vehicles, vehicle to grid and grid to vehicle, hydrogen storage. These are some of the mechanisms coordinating electricity and gas networks. This could bring in sector coupling solutions, improved operations in terms of improving the time frame in which scheduling is done, having better demand and RE forecast, creating new market products like flexible RAM products and so on, having shorter gate closure for the markets. That is, rather than having a 4-hour market closure, we could do market trading in a shorter term time frame of maybe 3 hours to 2 hours framework, or even 1 hour for some of the services, if not all. Demand response, which is one of the cheapest option, can be there to provide grid flexibility. The disadvantages obviously are the quantum of investment and the management required, but they are quite cheap, and it is a reliable source to provide grid flexibility. Investment obviously is a costly affair, but that is one that is presently being adopted in a big way. Generation side flexibility can be brought in through increasing the ramping capability of units of thermal power plants, gas power, bringing in more gas power plants, decreasing the technical minimum of the grids, um, lowering down the minimum uptime and the downtime of the power plants, lowering of the startup and shutdown times. These could be some of the solutions to bring in more flexibility into the grid. Also bringing in gas power plants as fast response. Hydropower plants are presently what are providing fast start resources as a fast start resources. However, gas power plants can also be brought in to bring in that type of flexibility. Moving ahead from that, reserve scheduling is another facet that as system operators and planners that we need to focus. So because of high RE generation, reserve scheduling has to be resorted to, in which uh, appropriate reserve planning has to be done into the grid, such that even of case of any variability, significant reserves are available in the system to manage the demand. This is obviously dependent upon good RE forecasting and uncertainty characterization of that RE generation. The sources of uncertainty in the grid, there are variety of those that could come from uh, the parametric uncertainties like forecast error, weather data error, historical data error. Temporal uncertainties could be because of data variation from one year to another year. The resources could vary. You could have a temporal uncertainty in what was the data available last year, what is the data available this year. Those type of uncertainties can creep in into the system. Structural uncertainties because we have a lack of simulations, we have lack of understanding of the detailed modeling of those power plants. Spatial uncertainties the uncertainties may vary from one area to another area. Measurement uncertainties which are dependent upon accuracy of the model data, which are dependent upon the type of sensors that we use and the calibration of those sensors. Handling those uncertainties is obviously dependent upon accurate RE forecasting, modeling of RE uncertainties, and increasing the operating reserves. This is how you can handle the uncertainties using demand response and energy storage. This is what is presently, energy storage is something that is presently being practiced. Demand response is something that would evolve in the near future. I think I'll close my session at this point. There are a couple of other slides as well, but I think in the interest of the schedule, I'll stop at this point only. Any quick questions, I'll be happy to answer. Any of the audience?
So when you discuss the frequency response and inertial response, and few of them were automatic, means handled, are mandated and are to be handled in an automatic fashion. Can you briefly tell us about the ways in which such mechanisms are enforced or implemented?
I'll be happy if you detail out your question slightly more so that audience can understand it. I understand your question, but slightly more clearer, or just repeat the question just once.
Can you go to that slide where where you taught us about the inertial responses and responses across different time frames for a range of frequency? Yeah, this one.
Yeah.
So among these categories, we have first three where automatic response is enabled.
Yeah.
Yeah. So I'm curious to know that how are these response mechanisms implemented?
These are essentially technical solutions one part.
Okay.
These come through inherently they come through the characteristics of the system. These are not provided separately. These come through the network. It's the system itself. If we talk about the inertial response, primary frequency response, or the secondary frequency response, essentially it would depend upon what type of system it is. Say, for example, when our system is highly thermal generation dominated, in those cases, thermal power plants have got large inertia of themselves. So
Yeah.
those power plants, whenever there is an inertial requirement, whenever there is a change in the frequency or change in the demand, at those points of time, because of their own inertia, these power plants automatically respond to those challenges and allow the grid to be operated in a seamless way. As compared to that, when we are moving over to, if the generation portfolio is significantly of solar generation, in those cases, since we do not have any rotational parts in the solar power plants, or for that matter, wind power plants, wherein the turbine is disassociated from the electrical grid, in those cases, those power plants are not able to provide this type of inertial and primary frequency response. So this is something automatic in nature, and it is not something that can be manually provided. Even if you want, you cannot provide that rotational feature in a solar power plant, neither can you provide any inertial support. So this is something that is inherent in the system, and you cannot force somebody to provide it on its own. Whereas as compared to this, responses like in the time frame, in a larger term time frame, like unit commitment, economic dispatch, and slow tertiary, like increasing or decreasing generation, that can be done in a longer term time frame manually and through market mechanisms. So that is the difference. This comes inherently, while the longer term time frame solutions, they are done manually, either through man or a machine. Maybe a computerized algorithm would do the decision making. Here, it has to become automatically through the system. They cannot be brought into the system by external means. That is what the point is. Does that answer your questions clearly?
Yeah, but it raises further questions in my mind.
Please.
Yeah, so by response, we are specifically pointing to any variation in the frequency of generation, right?
Yeah.
Response to that, right?
Yes. Yes.
And for thermal capacity, we do have it set for 50 hertz. And if there is a variation in that you mentioned would be handled by the inertial capacity of the thermal power plants.
Inertial requirements would be handled by inertia, by the inherent inertia of the system.
Yeah.
Secondary, primary, secondary frequency response, secondary responses, and tertiary responses. They, if you see, they are provided. Let me just get. I think this. No. The secondary control is something that we have typically follows the time frame of automatic generation control. So the automatic generation control feature of the thermal power plants that we all have studied, that is what essentially provides the secondary control. That is a solution that is already implemented in the grid.
In an automatic fashion.
Yes.
Okay.
There is a governor that is installed on the grid, on the power plant, and this governor essentially provides the primary control, that is in this time frame, and there could be automatic generation control mechanisms which would provide the secondary control in the system. However, the time frame, in this time frame, human intervention is not available. And
Yep.
typically, if you talk about this time frame, 0 to 5 seconds, it would obviously depend upon the the nature of the grid. If the grid does not have inertial capacities, it cannot provide it through any machine. It has to have it so that it provides the response on its own. Whereas as you go on a longer term time frame, these are the services which can be provided through external mechanisms as well. Say in the case of automatic generation control, because if say, let's say if the frequency starts going down, automatic generation controller would observe that and try to bring in more generation to the system in this time frame such that system power balance is maintained. Whereas primary frequency control, the governor control that is there, that is to an extent, and if you go to inertial response, that is to 100% extent, that is simply dependent upon the characteristics of the system. There is no mechanism. If it is a heavy generator, obviously it would, if it is a large power plant, large turbine of let's say 500 megawatt, that would provide a larger inertial response as compared to a turbine of 100 megawatt. So if it is there, it is there. And if it is there, it will provide the inertial response. If there is only a 100 megawatt turbine in the system, it would only provide inertial response of that size that is available. You suddenly cannot provide it from an external means as such presently. This is
So
the
what
challenge.
is, yeah, okay. So what does it mean by variation in frequencies over large time frames, like where the manual control is provided?
No. The variation in frequency does not happen in large time frame. Variation in frequency happens in a shorter term time frame. It has to be managed in a short term time frame, in this time frame of primary, secondary, and tertiary response. So it has to be provided maximum frequency variations can happen maximum in this frame, in this time frame. However, what happens is as soon as the automatic generation control starts get activated, the generation would be, I would say, generation would be increased. Let's say if the frequency is going down, in that case, you would bring in additional generation through secondary generation control or through tertiary control, or let me show tertiary control or generation rescheduling. So if you get into this time frame of beyond 15 minutes, 60 minutes time frame, obviously economic load dispatch decisions can be reworked. This is a slightly longer term time frame being indicated. Even if you can bring in that response within 15 minutes, it is sufficient for the system. It is sufficient. I'll show you that. It is sufficient, even in this time frame, it is sufficient to handle the grid variations. Frequency variations typically are arrested within this time frame, not more than 3 minutes. Beyond that, it goes more about balancing the power rather than balancing the frequency. So frequency recovery typically happens within this time frame of 1 minute or so. Now, it does not go beyond that, usually.
Okay. You also mentioned that the shifting proportions of our power generation from non-renewables to renewables.
Yeah.
And in response to this question as well, you mentioned that inertial response is handled by the system itself when the majority of the power generation is provided by the thermal units.
Yeah.
So in case where this majority shifts to renewable load, like solar power generation and wind power generation, would there be requirement for additional features or mechanisms into the system to address these three areas?
Obviously, that is something that we are heading towards. This is something that is a technical challenge of providing inertial support. Say, if you see some of the European grids like Danish grids, UK grid, where there is significant generation coming from wind power plants, there the inertial support is not available. So when the inertial support is not available, the regulator and the system operator has to identify mechanisms. And those mechanisms could be technical solutions as well as market-based solutions, such that that inertial response is provided in the system. Because if you do not provide the inertial support, the challenge is that because of any small disturbance, even if a disturbance is of, let's say, 1 megawatt, it would lead to larger frequency excursions happening in the grid as
Got
compared to a grid of Indian
that's
size. Yeah,
yeah.
please.
That's what my question was about. Means if you can throw some light on these kind of responses, automated, which are essential, means where the proportion of power or supplied by the renewables is pretty large. What sort of means implementations we have for initial response or primary control response?
There are the primary control has to be, obviously it has to be, the responses have to be provided faster. Some of the solutions that are practically being adopted is through providing battery storage to provide those support, battery energy
Okay.
storage. But
Okay.
that is
At
again
grid scale.
at a grid scale, obviously. So, but even that is not something that is really sufficient. So, what they are doing is, what essentially they are doing is, these type of services like inertial response, they have to be regulated. Either you make it a mandatory feature that all power plants have to provide this much of inertial support. So in case this is the type of requirement that is there, in that those responses have to be provided by the generators on their own, one of the solutions, or those generators secure those services from a market, from different sources like battery energy storage, like demand side, like any other, or from other generators as well. They could secure those services from other generators, from demand, or through battery energy storage, some of those possibilities that can exist in the system.
What are available possible technologies to accomplish this? Like battery management is
One,
battery banks is one such thing that you mentioned.
yeah.
But for
Uh,
grids of scales like that we have in India, and is there any system that is in operation today in India which provides this kind of response?
Unfortunately, inertial response is not on the focus of system planners as of now in India,
Primary
because the
controls.
gravity of the problem has not become so large.
Okay.
Uh,
Because thermal still is a majority of the bulk.
yes, yes. I think it will take a couple of years down the line when we will start facing this challenge in a big way. It will take us a couple of years to reach this, to see this problem in a bigger way. Presently, we are still away from this problem. This will come up in the future. It is coming up. Let me put it very clearly. It is coming up at present in small formats like oscillations.
Okay.
These challenges are coming up in the grid on a weekly basis. Every week there is one incident that is reported at, on an average, 1 to 2 incidents that are reported at the NRLDC and NLDC level because of significant ramping happening due to renewables, typically in Rajasthan. These incidents are becoming more and more frequent, and the grid operator is aware about the challenge, but it has not reached a very, I would say, a catastrophic level. But yes, they understand the challenge that if the next blackout happens in the country, that would essentially be because of this weak inertial response in the grid and the oscillations that are being generated in the grid because of these issues. This, I think, everybody in the grid is aware of as of now.
Okay.
And this
Yeah.
is the challenge
Thanks for
that is yet to be focused very clearly. They are trying to bring in solutions, but apart from battery energy storage, I don't think they have been able to focus, because demand side flexibility that can be brought in, but it will require that appropriate market framework, which is not in place as yet.
got it, sir. One related question, if I may ask. Means
Yeah,
not
I hope that would be the last, so that we shift to the next session.
okay, maybe I should give this opportunity to other participants. I'll park that question
No.
first.
Yeah, let the last question also come in, not a problem. thereafter, we'll focus on other questions as well from other participants if there are any. Yeah.
Okay,
Please.
for all the possible means we have for generating power, solar stands out because there's no moving component there.
Yeah.
And the raw output is primarily DC there from solar cells, right?
Yeah.
Yeah. So, don't you think that adjusting or controlling the frequency from the solar units, it's much more robust and automatic, and it should be least of the concerns there.
The challenge is that the proponents of renewable generators, they say, why should we be controlled? They oppose, unfortunately, the people who are investing, the renewable generator lobby, they decline to be controlled. Unfortunately, they decline. They resist the intervention of the regulator to be controlled.
No, by control, I mean controlling the frequency of generation, like 50 hertz that we have as a prescribed AC frequency here. So that should be least of the concern in case of AC.
Yes,
in case
I got your point. Essentially, even if you want to provide those services from those renewable generators, that will entail a cost for them.
Yeah, sure. Yes.
So these RE generators do not want to face that cost as well.
If
don't
they
want to
are
do
getting
because
compensated suitably, that's a question more than for a regulation framework to
yeah.
address.
So if
Right.
if until and unless the regulator brings in a mechanism to compensate them suitably, these services will not come up in the system. So you have to devise those appropriate regulations so that those services are provided. Somebody has to be, either you mandate it or somebody has to provide it for money.
Okay, got it, sir. Yeah,
Either you
thank you.
force them or you provide them some money so that those services are provided. I totally agree. I totally agree with this facet that all generators should be providing those system services which other generators are providing. So if thermal power plants are providing inertial response, solar power plants should also provide those type of services. However, in the guise of promoting renewables, the systems are resisting those solutions, and maybe over a period of time those things will come up.
Yep, thank you. Thanks for your comments, sir.
Yeah, any further questions? If there are any, I'll be happy to take up. That was an interesting set of questions. If there are no further questions, I think I'll stop. We have next session to be brought in line. Dr. Satish, is it fine?
Yes, sir.
Yeah. Thank you, all the participants. I understand it was a slightly more sketchy presentation on from moving from planning to operational perspective. We started a bit late and I thought of covering it in a slow fashion. However, I'll be happy to take up these points. If you want, I can respond over email or maybe any other session. I'll be happy to answer those questions. More focused on planning studies and more focused on system operation studies as and when required. Thank you for your attention. Thank you very much. I'll end the session, Dr. Satish, then.
Thank you. Thank you, sir.
Okay.
Hi, good morning.
Good morning, sir.
Morning. So today is our last day, and I will focus on some more advanced mathematical model for the optimization, like how to look at certain problems. So what I have done so far, I will discuss about those, so that you get that knowledge as well, and you like may be able to understand it more properly. Like some mathematics is there, then how to read it, what are the significance of those, so that when you are doing some your own research, you should be able to create your own models based upon the different assumptions you have and all, right? So today we will talk about like one of the cybersecurity attack model, like how we can design a attack, and that attack modeling is not from the communication side or computer science point of view. It is from the power system point of view. Okay, so let me share my screen. So to understand like some attack modeling, let me, so let's say we have a power system. Okay, and in power system we have the entire network, and different loads are there, different generators are there. So let's say some power system is there, and some information is fed to basically our control room. Okay, so control room is continuously monitoring the entire power system, and he's getting all the information from the physical power system to the single control room, where it will run the system operation like dispatch related programs, and like for the fault, like if there is some fault and what are the different system states. So all related, and that information it will run. So let's say I am assuming that certain demand is being basically observed from the power system, that this is going to be the demand in the system, and in control room we will perform some optimization. So let's say cost minimization. It can be your economic load dispatch, or it can be your OPF basically. Okay, so that optimal power flow will be performed there, and you will get some generator schedule. Okay, so some generation schedules will be provided, and those generation schedules, based upon whatever demand we have obtained, we will provide some generation schedule. Okay, so let's say the PD note is the real demand in the system, and by PD note, it does not mean like total demand. It is basically uh, at each and every node what will be the demand. So that is PD node, and then all the different generators. So we obtained a particular schedule with the help of our DCOPF or ACOPF, and we set those generators to the this updated schedules. Okay, so this is the very simple symmetric diagram. Now if we talk about attacker's point of view, so there can be multiple objective of attacker. That attacker can gather certain information, he can manipulate certain information. Okay, and there are many places where he can attack. Okay, so let's see, certain demand is basically observed in the system, and that has been sent over the communication channel to the control room. If an attacker basically comes into and modify this particular demand. Okay, so some whatever is the demand, he is just modifying it. So in the real system, demand is still a PD note, but for the control room, it has been falsified. So these kind of attack is called false data injection attack. That whatever is the actual data, we are uh, perturbing that data, and certain false data is being basically inserted in the system. I think I'm audible. Yes. So based upon that new demand, the generation schedule will also change. So instead of PG node, we will get, let's say, PG attacked vector. So instead of PG node, which should be the optimal schedule for the our existing current demand, but as the demand has been manipulated, the information which a control room will give will be the PGA, let's assume, like attacked generation schedule. And if those generation schedule goes into the real power system, then uh, so can you tell me what was the conditions of optimal power flow here? What we were optimizing basically in power flow? If you remember, we discussed DCOPF to a very large extent, and the common objective was like minimization of cost, and the constraints was like satisfying all the power flow limits. So OPF basically satisfy all the power flow limits, like that for a particular demand, the generators are dispatched in such a way that the entire system is running within its bound, whether it is voltage bounds or whether line flow limits. So but from the attacker's point of view, the demand has been changed. The generation will also change, and that may lead some of the line flow, like maybe the line flows will be changed because as per the control room, the demand is something else, but the real situation is different. So your line flow may be overloaded, your voltages may be overloaded, and once they are overloaded, whatever is their rating, if they are let's say operating above that, whether the voltages of the buses or the line flows, um, the relays will sense those information, and relays will automatically try to isolate that area. Okay, so this may lead to basically disruption of the service in the power system. And if the attack is designed in such a way that if it like some lines are very critical, okay, some lines are very critical, and if those lines goes out, the impact will be cascading, and if one line goes out, the entire power flow of that line will move to some other lines, and then maybe those lines will also get overloaded, and then those lines protection system will come into picture and isolate the second line as well, and this process or basically this entire effect can carry forward, so a cascading effect will be there, and it may leads to the entire collapse of the system. Okay, so that is like one of the major like you can say, if this kind of attack is can be realized, it is the entire service will be disrupted, and that leads to very catastrophic you know events. So there was, I think, in 2015, the entire like most of the Ukraine power grid was under attack, and that was during winter time. So lot of consumers basically were out of the electricity, and during winter uh, basically the temperature was very low, and they have to suffer a very like they have to bear the very cold winters during that time. So that is the one thing. Let's say for the countries like India, um, if we don't go for the like discomfort, still like the electricity is the backbone. If it goes out, the entire system will be basically on the hold. Now all of your financial services, banking services, everything goes like left, they will be put on the particular hold and stop. So that leads to a very good amount of financial loss as well. Okay, so different kind of like attackers can have that influence. So this kind of attack is called false data injection attack, FDIA. Okay, so we will just look at the mathematics of it, like how one can create or designs such kind of attack, and what information he's going to attacker is going to need, for to create this kind of attack. So let's say certain assumptions if I make. Okay, so first assumption if I make is that just to make these kind of attacks bit realistic, the first assumption I will make that generators cannot be attacked because generating stations are few as compared to the loads. Loads are very large in the number, and we generally protect our generating power plant. So we assume that there can be no attack on generating stations. Okay, so that is one quite realistic assumption that there are no attacks on the generating stations. Uh, Loads and line measurements are on attack. Okay, so that is another assumption that the attacker can target load measurements and line measurements to design a particular attack. So this is one assumption that loads are on attack. Then apart from that, you know, to make it this particular attack more realistic, let's say another assumption is, it's not necessarily, but to become stealthy, like we the attacker has been attacked on the system. But whatever, let's say, okay, so we're talking about this particular demand and some manipulation has been done, and that manipulation is sent to the control room. So attack can be on the meter, which is measuring this particular different loads. So it can be on the measurement units. It can be on the communication channel to manipulate this information. Okay, the demand information. Now, let's say there is a load of 50 megawatt and attacker change that 50 megawatt to, let's say, 100 megawatt. But if goes if it change that load to a very large extent, obviously the control room also have their own bad data detection. Sometimes what happens that through communication sometimes data is corrupted. So they look for the bad data, that some data may be bad, really bad, because of the communication glitches and maybe measurement errors. So they look for those bad data, and they have a history that, okay, generally like different loads have different um, history of consumption. So if it is very weird, it will be easily identified, and the attackers will not be able to achieve their target. So one assumption is the deviation in the load, the load deviation are small. Okay, so that is one assumption, that attacker will inject some deviation in the load, but to a very small quantity, not much as such. Then apart from that, what happens that system operator also knows total demand. So the individual demand forecast is there. Apart from that, the total demand forecast is also there. So let's say I have hundreds of loads, and if a attacker injects that, okay, these deviations are small, so let's say plus minus 5% or 10% deviation is provided to the existing loads. So if somebody's let's say 50 megawatt load was there, so 10% will be 5, so it has been increased to 55. Okay, so if all of them are increased and the deviation are positive, then the overall total system demand will increase to the same 5%. But what happens that, like, all the loads does not deviate in the same direction most of the time. Like if we talk about the rational behavior, some may be increasing the demand and some may be decreasing the demand, so the total demand forecast will be different. So generally, like, to make it more realistic attack, the algebraic sum of the load deviations should be 0. So these are like some other assumptions. So if we put this particular assumption that the load deviation, which is basically I can write it down like delta PD. So if the change in demand, the algebraic sum, if we make it equals to 0, then the total system demand will not change at all. Whatever is the current demand, it will remain the same. Okay. So this basically like for from the control room point of view, there is no change in the demand if we make this particular assumption. And if we have to achieve this kind of attack, some of the loads will be like some have the positive deviation and some will have the negative deviation. So that's why this kind of attack, when the total change or algebraic sum of the deviations or attack, if that is equals to 0, these are called basically load redistribution. That attacker may increase one particular load by let's say 10 megawatt, and then he may decrease 3 or 4 loads to compensate that 10 megawatt. Okay, so that like total so the total deviation will remain 0. So we are basically redistributing the load, so increasing one load and decreasing another loads. So these are load redistribution. So if this condition is there, these attacks are also called like LR attack. Okay, so these kind of attacks are called LR attack. Now if we look at the different mathematics and how attacker can create this kind of attack, so first of all we have to look at the objective, what can be the objective of the attacker. Okay, so what can be the attacker's objective here? Like suppose if he wants to attack on a transmission system, and he wants to like, so the attacker can have a multiple objective. One of the objective is to just gather information. So in that case he will send some spywares, and he will observe like the consumption patterns, and what are the different parameters. So everything he will just observe, and he will do no harm to the system. So those kind of attacks are generally called spyware attack, and it was just to gather the entire information. Once the entire information is gathered, then he will execute its real attack on the system to harm the system. Then objectives can be so who can be these attackers. So let's say if we are talking about making some financial gain out of the system, so load itself can be the attacker. That a load is there and he's like attacking or manipulating its measurements. So whatever is the consumption, real consumption, it may basically decrease its real consumption by increasing some others consumption, attacking the other meters of the a neighboring nearby. So and that too gain the some financial benefit. But if those kind of attacks are there, uh, if attacker that kind of attack is realized, and if the deviations are very much large, um, it's quite easier from the like state estimation and the bad data detection techniques to identify those kind of attack, that okay, this particular user is doing it. So generally those attacks are not practical, because to gain very small financial benefit out of it, and for long term you cannot be remain hidden, like so uh, system operator will know over the time that okay, yes, the measurements has been manipulated. So in that case they will be able to identify the culprit, and they will put a very large penalties on that one. So generally these kind of attacks are very rare. But suppose some current geopolitical situation, maybe some enemy country or some other country can attack the uh, let's say in our grid. In that case they will try to disturb the system. And how they can disturb the system, so let's assume they will go for the like overloading the particular lines. If they are able to overload a particular set of lines, then their protection system will come into picture, and that protection system will um, you know trip that particular line or isolate that particular line if it is overloaded from the system operator or system point of view. And then it may leads to a cascading effect and disruption of the service to the some of the users or the entire system as well. So generally, like for this particular modeling, I am considering like maximization of uh, power flow is basically one of the attack objective, like maximize the power flow in the particular lines. Okay, and the variable will be delta PD, like changing the loads value. So the what can be the different conditions? So one condition we have already made, that summation of delta PD should be equals to 0. Okay, so that is one condition, like for all d equals to number of the demand, and that overall change will be 0. So this delta PD, capital D, is basically like I'm using as a matrix, it's a vector, and that will be our attack vector, okay, on the system, that okay, this much load should be changed, and that load will be changed in such a way that it will leads to the um, overloading of a particular or few or maybe the entire system's lines. And if the lines are overloaded to some extent, generally like 15% above the rated value, the protection system will come into picture, isolate the particular line, and cascading may happen. If you look at the another assumption, the load deviations are very small. So if we use that one, so we have to put that as well, that whatever is the deviation, it should be basically some plus minus of the actual demand. Okay, so I can put like the initial demand and whatever is the my demand. So I will put this particular condition, like for all the demand, the deviation should be, let's say, plus minus 5% or plus minus 10%. So that is the deviation provided, and this alpha basically is the value, whether it is 5%, 10%, and 15%. Okay, so let's say once we have realized this particular kind of attack, that we have changed the load, that will change the line flow. So the line flows can be basically placed like the generation shift factor matrix. So generation shift factor matrix and multiplied with the power generation minus uh, power demand. Okay, so okay, wait. This is the line flow. So this GSF is basically generation shift factor. It is defined basically like if certain generation is injected at a particular node, then how it is going to be distributed over the entire length of lines. So or over all lines, how it is going to be distributed. So this factor gives you that. So here we are multiplying it with the generation, and that generation multiplied with the GSF factor will give you the line flows. At certain buses, generators are not there, load is there, so we can consider that the loads are basically negative injections. So generation are positive injection. So that's why I have placed it with the minus sign, that the loads are negative injection, and this is overall like PG minus PD is overall injection. And if I multiply with this GSF matrix, it will give me the load or basically line flows in the entire system. Okay, so once we have obtained this one, so this is like the initial power flow. So if I so this is how we can calculate the power flow. Now I'm not going to use this particular constant. I will look at the, so we will not use this one. I can place a constant that change in load or line flow will be again some GSF matrix, and whatever change we have provided as a in the load. So this is what we will see, that what is the change in the load. If we are able to identify this change in the load, then multiplied with the GSF will give you the change in your system, or basically the line flows. Okay, so these are basically one of the condition that okay, these are the line flows, and this change in line flow will basically be given to the okay. Apart from that, we need this. Okay, so let's say some modified generation is coming in the system, some initial demand is present in the system, and then we have basically inserted some delta, so that is plus some delta uh, PD that has been inserted, and if you multiply we will able to calculate the actual line flow. So that is basically my PLL. Okay, and PLL is basically this L represents here, like this L is for targeted line. Okay, so this small as targeted line, and PL is the entire vector. So maybe we are targeting a few of the lines, so that L can be like one or two or three if there are three targeted lines. And if it is one targeted line, like okay, I want to focus my attack to target a one particular line, who that, and it is like by observation it is it can be realized that uh, which lines are critical. If those lines goes out, the most consumers or most customers will be affected out of that line basically. So we can pinpoint our attack to target a single line, and maybe the like isolation of that line will leads to the cascading effect. So that is like targeted line, and so power flow we can calculate from here, and change in a line flow we can calculate here from here. Okay, now once it has been identified, let's see how many meters he has to attack. So let's say some uh, define some variable, binary variable, so it is 1 and 0. So this can have a value 1 and 0, and if your delta uh, PD is not equals to 0, and this is if delta PD is equals to 0. If change in like for a particular load or demand D, if change in load is 0, then we don't have to attack that meter. So this 0 and 1 or this delta will give you the information that which or which demands needs to be attacked, and respective values will be created equals to 1. So this delta PD is not equals to 0. So it means like we have to attack this particular meter or measurement. So this is one thing. Another thing is to remain hidden. If we have attacked on the load, and the generation is obviously like manipulated schedule, if we overload them, superimpose them, there will be always a change in the line flow, and that change in the line flow again, like with the help of the measurements, it will go to the control room, and control room have some other line flow measurements from the whatever DCOPF it has sold. So the control room will be able to see that okay, some attack has been there because some data has been manipulated and we are not getting the equal result. So to hide the attack, we have to also manipulate the line flow measurements. So let's say which line flows needs to be attacked. So that is, let's say PLL. Okay, and which lines needs to be attacked. It will be decided if your delta uh, PL is not equals to 0, and if my delta PLL is equals to 0. Okay, so depending upon the, if this is not 0, it means there is no deviation in the line flow. So those meters are not has those meters we do not the attacker is not going to attack. If the line flow is deviated, then we have to attack those respective lines meters so that the system operator does not know about it. So this is the another variable. Okay. Apart from that, if we look at that, like how many total number of meters attacker needs to attack, so that will be summation of delta PDD and over D and plus summation of delta PL L over L. So these many attacks attacker has to attack if he wants to realize a particular attack. So this is the model of the attacker, that he has to attack particular loads. In case of lines, basically we have for a line we have a sending end and receiving end measurements. So to manipulate the line flow, he has to attack 2 meters. One is two measurements, one is at sending end, one is at receiving end. So for each line I will multiply it with the 2 as well. Okay, so those many number of meters it should attack. Is there any doubt so far in this formulation? So this is what we have the objective we have identified, that it is going to attack the flow of the actual flow of the system, line flow lines. So this is defined by PL to keep the attack stealthy, and like the system operator should not know about it. He will put a constraint on this, that the delta PD summation of delta PD or the algebraic sum should be 0. That is load redistribution. Then the division should be very small. So he will not change the demand to a very large extent. It will change only to a certain plus minus 5 or 10% or maybe 20-30% variation from the actual demand. Okay. Then once this these two constants are placed, and then delta PD will basically leads to the change in line flow, and then change in line flow will identify that how many number of meters he is going to attack, and then adding of these meters, these many total number of meters he has to attack. So attacker can have a condition that he cannot attack the entire system, because the limited resources simultaneously attacker has to attack all of these measurements. So let's say some resources here that okay, he can attack at 50 location, or let's say he can attack at 10 locations at a time. So we will put that the total number of meters attacker can attack is 10 only, 10 or 20 and so on basically. So this is the model of attacker for a simple load redistribution attack. Okay, if there is any doubt in the mathematics, you can ask.
Would you redefine, sir, alpha and R?
Sorry, alpha and
R, the last constant R.
yes. So alpha is a deviation. Okay. So PD is actual demand for a particular load D. Okay. So let's say 50 megawatt is the demand for actual load. If a attacker creates an attack of, let's say, change in attack is 50 megawatt plus 50 megawatt. So the overall demand will become 50 plus delta PD is, let's say, plus 50, then it will become 100 megawatt. Okay. So the demand will be doubled. So if that information goes to the control room can easily identify that, okay, generally this demand does not vary that much significantly. So they have this bad data detection tools, and they will say that, okay, either the communication failure was there or some attack was there, because this demand is too much high. So to make the attack stealthy, the attacker will try to change the demand to up to certain percentage. So either let's say if alpha value is let's say 1.1. Okay. So if alpha value is let's say 1.1, then he will basically put
10% overloading.
10% one. So it is, let's say, 0.1. So whatever is the demand, so the demand was 50, let's say, and I'm using 1 or generally 10%. So 10% is like 0.1. So 50 into 0.1 will be 5. So delta PD can have maximum value of 5 or minimum value of -5. Okay. So if 50 demand is there, the +5 can be there and -5 can be there. So the demand range or basically attack range will be -45 to +55. Okay.
Yes, sir.
So this alpha
Yes.
dictates the small deviation, like how much small deviation he can put. So let's say if we assume that the bad data cannot detect 5% deviation or 10% deviation, then we will use this alpha and to decide whether the attack will be feasible or not. First of all, okay. So from the attacker's point of view, we can do this. We can do this from the protection point of view as well, that we can identify certain lines and we can target each line at a time and design our own attack from the system operator, and then we will know that okay, these lines are very critical and attacker can easily attack by changing certain loads to, let's say, 2% or 3% or 5% as well. Okay. So from the protection point of view as well, we can identify like which lines are critical, and with a very small deviation they can be targeted. But from attacker point of view, so the first line of defense is to uh, analyze and model the attacker's behavior, like how the attacker will identify that which attack he should inject. So first line of defense is model the attacker's behavior. So this is what we are doing, that like attacker is going to make a decision like this, that he will target a particular line, he will keep the deviations close to zero, and so deviations very small. Overall resultant deviation or the summation of the deviation should be zero. And then these are like simple our DCOP of constants, that this constant will give me the delta PL change in the line flow, this constant will give me the actual flows in the system, and then we will identify like number of meters. To go with the last constant, it is basically resource constant. Resource condition. So attacker can have some certain limitation on the resources, like he can attack 10 or 20 or 30 meters simultaneously at a time, not more than that. So in that case, I will put, let's say, r equals to 20, that he can only attack 20 meters. So I will put that condition as well from the attacker point of view, that the number of deviations should be in such a way that the total deviation should not be more than 20, because he cannot attack more than 20 meters at a time. So this is a resource constant. Okay.
Yes.
Yeah. So the thing is, like next part is from where he will get the PGA, because it is post attack information. So once he will realize the attack, then only he will able to know what will be the modified or falsified generation basically. So in the same model, so that is one objective. Within this objective, one constant will be system response. So attacker will basically model the system response as well. Okay. And system response is generally, like we perform a DCOPF to schedule the generator. So I will put that constant here, that minimization of n equals to 1 to ng and some Cn and Pg. Okay. So let's say this is g equals to 1 to ng. So this is the system response that it will solve for the post minimization. The conditions in here will be that our total generation g equals to 1 to ng. So whatever is the Pg should be equals to the total demand. So d equals to 1 to nd, and whatever is the total demand. This demand has been manipulated. Okay, so this demand is basically whatever the initial PD note plus delta PD. So this is the total demand. Okay, apart from that, we have to calculate certain line flows. So I will calculate the line flows from the system operator point of view. That will be GSF, the matrix. Okay, and then whatever is our this PG, which is the outcome of the optimization that the system operator will give you the generation dispatch PG minus. So the PD node should come here. Okay, plus some delta PD has been inserted as well. So this will be the total power flow for the system point of view. Okay, system operator point of view. Then further, if we see, is basically
Sir, what does square brackets mean?
it's a matrix.
Okay.
So instead of like writing down the PL is not a single line, it's basically set of lines. That's it.
Yes.
So square matrix is basically like I'm solving them in a matrix form, and PG this PG matrix is basically like generators at all the nodes. Okay, if there are no generation, that will respective value will be 0. Same goes with the demand. If some certain demands are not there on a particular bus, that value will be 0. Okay, so we are writing it in generalized way. These brackets are basically matrix. That these are vectors, not a single entity. Here I have placed it like like the
Yes.
individual demand. So okay. So once we have obtained this one, then we can write down that this PL vector will have certain maximum limit, PL maximum, and will have certain minimum limit. What will be the minimum limit on the line flow?
0.
No?
Minus PL. Yes. Minus
Yes.
PL.
So we can discuss that one, that it will be the same maximum but with a negative sign. Let's say the PG is also be like whatever is the PG max, maximum limit of the generators, and then PG minimum limit of the generators. So this will be the system response. Now so we will have a upper level problem, and then we have a lower level problem, that attacker will try to optimize this particular objective, and in bottom basically he will mimic the system response as well, so that he obtains the PG, and then he will use that PG here. Now what will be the actual power flows in the system? What will be the power flow in the actual power flow in the system?
DCOPF results.
No. Look, the DCOPF is performed on this falsified demand. Okay, so the actual demand here is basically like the demand is PD node, and because of this falsified information, the generation is now PGA, attack generation, because this has been falsified. So this PGA is basically modified, and the power flow will be because of both of these two components. So what I have mentioned here is actually not correct. So what I will do is, let me erase this part. It is not part of it. Like the power flow will be whatever is the attacked generation or falsified generation minus the demand itself only. Is this okay? Okay, so this is PD, and then so this is actual like line flows, and then we can basically the rest of the things will remain same. So the thing is how to solve it. Very important part is how we can solve this kind of like formulation. So basically one optimization is nested under another optimization. So one, we have maximization of the line flow, and another is basically minimization of the cost. And the minimization of cost is nested under the maximization of the power flow. So to solve these kind of basically nested power flow, there can be multiple ways, and it is basically like assuming certain values constant at each level. Okay, so both level we will assume that whatever is the coupling variables, like here if you look at this delta PD is the only variable which is going to be supplied from the upper level to the lower level. So if we assume certain fixed value of this delta PD, then we will get certain attack PGA, and that PGA will be used here, and then we will obtain the new PDA, and back and forth we can solve it. So that is one way of doing it. Another is like we can write down the KKT conditions of this particular entire problem. Okay, so for the DCOPF problem, we can write down the KKT conditions. So KKT conditions will provide the final solution. So write down the KKT conditions of this problem and place it with the first objective. So that is the another way of solving it. Okay. Do you have any doubts, like to how to understand a model, let's say from the mathematical model for the attack? So I will not go much into detail. It's only two level. We have solved sometimes, like third level as well. But I will not go into that. So sometimes the problems are tri level. That uh, first the attacker will basically assume that he will develop the attack vector. With that attack vector, he will calculate the modified generation. Okay, but once the generation has been modified, those modified generation will change the entire power flow, and in that case he have to look for the critical line which he needs to be attacked, or the critical line which needs to be attacked, and then that information will be used to hear like which line to attack. So far we can like solve this bi-level problem for n number of lines, and like for line 1, line 2, and line 3, and see if we are able to overload a particular load or not. Or sometimes like we can also add one more optimization below and identify that okay, this critical line will also be identified with the help of the objective function. So I think this is it on the this particular segment, like how we can understand the particular problem of the cyber attack from the power system point of view. We are not talking about like communication or the computer science point of view, that how these attacks will be realized. We are assuming that this, yes, as if some attack can be realized, what value of the attack should be there. So what should be the attack vector? Okay. Uh, now, certain so I think yesterday some storage related modeling has been discussed by Dr. Deep Kiran. We will delve much, you know, depth into that. Let's see. So let me give you one very recent problem which we were working on, and it is very good optimization problem. And you will see like how much depth can be there in the particular optimization problem. So So let's say we are talking about the energy storage. The first is what is the capital cost of installing energy storage? High or low?
Right.
So I will use energy storage system. So yes, thank you, Swati. So usually it is very high. Now let's say we are talking about a local community where some distributed generation is there. Let's say some wind farm is there, some solar producer is also connected, some loads are also there, big loads are there, and all of them are they need basically certain energy storage. So if they install, let's say there are only three parties. One is your solar, one is your wind, and one is your consumer. So if these three parties are there, and if they install their own storage, then what will happen? Like the own and the entire storage will be there. The three storage needs to be installed, and very high capital cost will be very high. So very high investment is needed for three different storage. Now the thing is, uh, what is the use of storage basically? I think that was discussed by Professor Bhaker as well.
To provide inertial support or primary frequency response support
Yes,
in
but
case of renewables.
yeah, in case of renewable, it should provide the like some certain inertial support. So that is if I'm looking at the problem from the grid point of view. But if we look at the problem differently from the individual players point of view, whether it is, let's say, renewable power producer. So let's say we have a wind power producer. So it has variability, we understood, and because of that variability, we need the inertia support from like grid also need the inertia support, right? Just to overcome that the imbalance created by the this renewable production. So don't you think that it is the duty of the wind producer or the solar producer to balance its own schedule? So whatever schedule is provided, it should stick to that schedule, even though there are uncertainties behind it. Why
They
it is burdening the system?
they will be needing inertial storage
Yes.
facilities
Yes, so
because
let's say wind producer is there, and if he has certain storage, so obviously the wind powers are variable, so he will have certain dispatch. If it is producing some extra power, the basically that can go to the storage, so it can charge its own storage unit and maintain the fixed constant output. Whenever the power output is low, he can use its own storage and supply that power, and maintain the perfect balance.
yes,
Okay, so that is possible. And another way, basically, we discussed that market based solution, where we discussed that imbalance cost minimization. So he will try to come up with the schedule which is the expected schedule, which will leads to like if it is varying too much high, then some penalties will be there. So to avoid those penalties, it will give a perfect dispatch, and that dispatch will try to be cope up with the variations. So that will be like kind of average value of the variation, so that it can handle the uncertainties. Another way is he can install a battery energy storage system. So battery energy storage system has the balancing support. He has the balancing feature, so he can balance out the output of a variable producer. Correct. But we discussed that capital cost is very high. So today we can like I can provide you example that, let's say, this is how we create the battery, right? So let's say a large energy storage is there. Okay, one more thing is, so these individual participants, what is the utilization factor of the battery? How much they utilize it? Okay, let me ask you, do you have inverters? I think all of you have have inverters at our houses. How much do we utilize that? What is the utilization factor of those batteries which are connected with our inverters? Very less. So we don't need that investment, because powers are like we are getting power continuously in the cities. So those inverters are not needed to the very large extent. Another thing is uh, the need of battery is varying with the different source. So we can understand that wind power producer produce most of its power in the early morning. Okay, कि वहां पे इसका प्रोडक्शन ज्यादा होता है. Solar produce in the afternoon. So they basically compensate each other, the solar and wind. Okay, and even the load as well, they if we overlap all the like loads, wind, solar, and different participants, they have different profiles, and they need the battery at different time frames. Not maybe if wind producer needs a battery storage service, and the other maybe the solar at that time or the consumers at that time may not need the battery storage at that particular time. So why having multiple battery storages? We can have a one battery storage. So that's why I am assuming that let's say large battery storage or the energy storage system is there, and upon requirement, they can, let's say, this particular part is provided to wind power producer. Let's say this much section is provided to the solar PV, and let's say this is kept for the consumer. So instead of having three distinct energy storage, we can have one storage, and they can all can share it. Okay, so they will all share this particular storage because their requirements are not overlapping. Is this clear? Okay, so that sharing is basically uh, leads to the allocation of the rights. Okay, that how much rights a person can acquire from the battery storage, and depending upon the needs he can get the rights. So let's see different players. So what can be like, let's assume a local community. Now to keep the entire problem too much generalized, like not restricted to the wind or solar or the consumers, and we are looking at basically at market driven solutions. So let's assume arbitrage is also there. So if there's some battery storage is there, and if it is available for sharing, that somebody can pay some price and access this particular storage, part of the storage, not the entire storage, and at different time frames. Then some aggregators may also come into picture, and those aggregators will try to acquire certain battery. So what is aggregator? Aggregator is basically like some entities which make a profit out of the price difference. Okay, so they sometimes buy at a cheaper prices and sell it at the higher prices. Um, Here, if battery storage is there, what aggregator can do is he can buy whenever the in the during the entire course of the time period, whenever the prices are low at the certain times, then he can ask the storage to uh, store that much power for himself, and then he can sell it at the higher prices. So he can also make the money out of this particular opportunity. So let's keep a aggregator as well, and we will discuss different participants. So let's say different participants are there, and they try to acquire the rights in the particular community where one large storage system is there. So what can be the constraints basically? So one constraint is, let's say PC ith player needed the charging rights. Okay, or suppose some ith player is there and he needs to charge at particular time t, and let's say that player is basically utilizing the I at time t. So this is PC max I at t is basically charging right. So a player can acquire certain charging right, uh, charging right of player I at time t. So a player can, and by means of player here is basically your wind producer, your PV consumer, aggregator, and you can basically have a number of players. So a player can, depending upon its own requirement, irrespective of the system, he can acquire certain charging that okay, I'm going to charge the existing large storage um, for a like particular time t. Okay, so for to use the basically charging function, or basically to charge a battery at particular time t, he has to acquire certain charging rights. So if he's acquiring certain charging rights, based upon the whatever is the charging rights price, he will pay certain money that okay, I'm paying you this much and you have to perform a charging action for me. So instead of like um, mm, let's say for wind power producer, if we talk about, if he has some excess power, he can ask the energy storage to store the excess power which is a wind producer is producing. So he will acquire certain rights that okay, I'm acquiring the rights, and those are basically, let's say, the PC max. Similarly, whenever the power is less for a wind producer, let's assume, then in that case he will need a discharging rights. So that time will be some different time. So let's assume that is the PC max I t. So these are the rights he is like the producer is, or wind producer or any player, I'm keeping it generalized. But if we understand from the wind producer point of view, if the power dispatch, a certain dispatch is there, if you because of the variability, if it is producing less power, he will ask the storage that okay, you have to discharge for me. Okay, the quantity will be this term PCIT or PDIT, and the maximum it can provide is whatever the rights he have basically obtained. If he has obtained the rights of certain quantity, up to that quantity he can ask the storage to basically discharge or charge. The same can happen with the basically energy as well. So EDIT, and that should be ED max IT. So similarly, I can put that this PD max is basically discharging rights, or ED max is energy rights. Now the thing is, do I need three rights, or do I have to pay for three different rights? What do you think? Should a player pay for three different rights? Swati, Gaurav? Today, right holder pay for charging, discharging, and energy rights, like all the three rights. So the thing is, let's say a lot of players ask for charging at the same time. Then the physical, like the energy storage has certain physical limitations. He cannot provide, like let's say 10 or 20 players ask that okay, you have to charge for me this particular time. Then he will let's say the overall charging capacity is more than whatever its charging rating, then he will deny it that okay, we cannot do it. So based upon whoever is paying more, based upon that, like charging rights will be given. So the charging rights need to be acquired. Same goes with the discharging as well. That if lot of player ask at the same time to like multiple players ask to discharge at the same time, it will be restricted by the actual physical capacity of the energy storage. That okay, it can only discharge this much quantity. So that's why they have to acquire discharging rights as well. Uh, Another thing is, let's say at a particular time, let's say time equals to 1, somebody asks to charge certain quantity, then time number 2 somebody else asks for the charging, and so on. If everyone is asking for charging, then the energy storage will basically have a energy capacity as well, SOC limits as well, like so it can have certain maximum SOC and minimum SOC, not more than that. So in that case, what will happen, that certain energy rights, like okay, some player asked to charge at a particular time and then keep it stored for certain duration and then discharge at some another time in the basically the entire course of the day. So that energy is basically stored there for a particular player, for that for the to be used by that particular player. So uh, the energy storage will charge for energy rights as well. Okay, so once we have like these constants has been identified, we have to keep a look on the SOC as well, like how much is the SOC. I will put that energy is basically at any time t will be, let's say, whatever is the initial energy at any time t for player I, or its initial energy, so it is at actually sorry, t naught, then some charging coefficient, okay, charging efficiency, and then we will have some PCIT, that this is the charging has been done. Maybe some discharging is there, and that will be divided by some neta t. So discharging will be reduced, and this is what we can write down for the particular like we keep a record of energy, like how much has been charged on behalf of ith player. Okay, so once we have done this particular part, we have to place the yeah, that's it, I think. So these are the few constants. I will not make it complicated with like the real time and different market spaces are there, so different floors are there, so it will be basically more complicated. Now, these are the four constants that okay, some player has acquired some charging right, discharging right, and energy rights, and for those rights, basically, he can utilize up to those rights to charge, discharge, and store certain energy, and energy balance can be provided like this. So this is with the initial, uh, let's say at this constant can be written when t equals to 1, and then e d I t is equals to e d I t minus 1 plus neta c p c I t minus p d I t divided by neta d, and this will be for uh, t equals to or less than let's say capital T. Okay, or we can say t is more than 1. So whenever the time, the initial time, whatever some initial energy existed in the system, it can be zero, it can be some value. You will use that at the beginning of the time frame. Otherwise, then you will use the last constant. So these are the some constants which are common for all players who seek I would say storage rights. Okay, so these are the some constraints which are basically common for all the players. Whoever is willing to acquire certain rights to use a large storage which is available in the system. Now, if an arbitrager is there, okay, so if an arbitrager is there, the objective of arbitrager will be to maximize the profit, okay, and the profit will be like over all time periods. It will have some, let's say, price in the day-ahead market, and then whatever it is discharging, and whatever is it is charging from the system. So this is basically has to like this particular part is the revenue of the. So I can put it like this. Okay, so this is nothing but the revenue minus he has acquired certain rights. So that rights has to be paid. So if he acquired certain rights from the energy storage, this will be paid. Let's say certain price is there, and that is for at particular time t, and this is, let's say, the charging price at a particular time t. So if this price will decide that okay, how much he wants the arbitrager, how much the arbitrager needs basically. So this is basically like how much he has to pay for the charging rights. Then similarly we can put it like PD max IT and multiplied with the price of discharging at particular hour t, and minus ED max is the energy rights at a particular hour t. Then it will be uh, multiplied with the pi e at a time t. Is there any doubt so far?
Lambda DA is day-ahead price.
Yes. So you know this is the day ahead price, or you can say some price at which the arbitrator is charging and discharging. So you can assume it is like the system price, or the price at which on which he is basically charging and discharging. So if an arbitrator is charging, he has to pay that particular price. So generally, like in this case I have assumed it's a day ahead price. It can be any price at which he is charging, and then he is discharging at the same price. So obviously it, like at the same time this PD and PC will not be possible at one time. Either he can charge or discharge. So both of them will not be available at the same time. Okay, so this will be the revenue, like he will charge, let's say t equals to 2, he will charge something. So this is the negative, or you can say it's a cost, because he has to pay to consume certain capacity or the power, and then he will discharge the same in the like whenever the prices are high, let's say like hour equals to 20, and so he will discharge it and make money out of this price difference. So this is the basically revenue of arbitrator. These three terms are basically cost paid to storage or rights. Okay, so these three terms are basically storage will ask that okay, you are utilizing this charging, discharging, and energy rights or facility from me. So this is much you have to pay to me. So basically, arbitrator will try to maximize the revenue and minimize the cost. So that's why minus has been placed here. Is this clear? Subject to the common constants. Common uh, constants which we have defined earlier. These constants basically. So he will try to solve this particular objective function. So the arbitrator will solve this particular function, and he will get what will be the output. Now let's say the next is for the renewable. Let's consider
The SOC constants will be that?
Yes, SOC constants are there. You can see it. Wait. Here, these constants are already part of it. Like these are common constants, right? So these will be placed here. So the
Okay. Yes.
arbitrator will make sure that SOC is within the limit. Whatever he has acquired, so he has acquired, let's say, this much maximum SOC. So whatever the ED, whether it like because of the charging and discharging action, its energy or SOC should not exceed this particular maximum rights which he has acquired in the system. Okay, at a particular time t. So
Yes.
arbitrator will
Thank
do
you.
this particular so like solve this particular objective. Let's say if I look at the renewable producer, so what a renewable producer will do, it will again maximize its profit, that is for sure. So maximize, and over all time t, it will also, let's assume the price is lambda dA, okay, at any time t, and he will produce some generation. Okay, so this ith player, let's say it will produce something, then plus apart from that he will basically what else a producer can have. So let's say as a renewable producer is also uh, acquired the storage, okay, certain charging, discharging and energy rights, which the like defined by the common constraint. So he can use those rights to charge it whenever he has excess power, and he can discharge it whenever he has less power. But apart from that, he can also perform the same capacity. Let's say maybe the scenario is in such a way that the whatever the wind is produced, it is close to the its actual dispatch or schedule. In that case, whatever the rights he has acquired are not useful, so he will also make money out of it. So let's say the PG is the variable that this much power he is producing in the real time, and then he will get some money at let's say time t, and that will be whatever he is discharging. Okay, whatever he is discharging, that much he will also get. So this much money he will get, that he is producing some quantity and directly producer, and he is also using the storage to produce for himself. So at a time he will basically get this much money. Now minus, I will not write all of these. I will put like cost of rights. It will be the same, this particular part, right? So these will be the same. Cost of rights will be there, and then subject to what will be the conditions it has to satisfy. So this optimization, he will solve this particular optimization subject to common constraints, whatever the common constraints we have defined earlier. Apart from that, it will have one more constraint, that this PG, how much it is going to produce, this will be basically less than, let's say, some day ahead schedule was there, and minus he will put some PC height. So if you look at this particular equation, let me change the color. That, let's say this was the final dispatch, this much it is producing. So he will sell some power in the market. So actually it means that some PGIT plus PCIT it is producing out of the total available production. Okay, so this it is directly selling in the market. So into the market, this part is used to charge. Okay, so this as PC is basically he is using for to charge. So if he has excess generation, let's say, so this is basically the obligation. PG is the obligation that he had certain dispatch and he is going to stick to that dispatch. And if the total production is more than that, the excess power will be used to charge. Then, if this power is less, obviously it is not going to charge it. So this part will become zero, and whatever is the capacity, it will try to supply the same power, and remaining will be basically discharged from the storage. Okay, so if PG plus PD is basically, if he has to produce something, then the production will be PG plus PD. And if he has to charge, so if the dispatch is less, he will utilize that, extra power to charge. And whenever the dispatch is more and he is producing less, then he will use the PG to the full extent, whatever is the capital G, and the extra power will be basically supplied by the PD demand, whatever is the discharge he is using. So this constant will be the extra constant, and the common constants are there. So the producer will try to solve this particular problem. Is this clear?
Sir, it's a bit difficult to understand.
Who's what's your name? Like,
Sir, Yogyadat, sir.
yes, Yagyadat. So just tell me what are the difficulties here.
This, sir, is the last constant one.
Last constant. So let's say this is the dispatch of the. Okay, so this is T1, T2, T3, T4, and T5, and these values are basically the dispatch. That this much he should produce, a producer. Okay, different levels are there. Okay, so this is I can draw it that time and dispatch. Now, if let's say the actual power, realized power is more than that. Okay, so actually the power for this particular producer is one is PG IT, then plus PD IT minus PC IT. So these are the actually I can say the PW. Okay, so he has to provide this much power only, and he has certain extra power in the first hour. So that extra power will be basically gone like this, like whatever is the let's say G1 schedule IT, and let's assume this is certain value, and plus that time he does not need to discharge anything because he has extra power and he will schedule this one, minus some PCIT, though extra power is used to charge the storage at that time. Okay, then
Yes, sir.
if it is lesser, then the PW will become whatever is the PGIT. Okay, so let's use capital G here, that this was the dispatch, actual dispatch at particular time. Okay, so actual dispatch will be whatever is the dispatch minus charge, so that will be provided equals to PW. Actually, like whatever is the production, that production will be used in this way, that he will fulfill this particular schedule and extra power will be used to discharge. Whenever there is a less power, then at that time it will only charge and there will be no charging action, it will discharge. So you can see here, by looking at this particular constant and this objective part, if he has some extra power, that extra power is, so he has total dispatch of something, let's say okay, let's talk about 100. So the actual production is 100 and dispatch is, let's say, 90 only. Okay, PG should be 90, right? A generator, let's assume, has a actual production of 100 megawatt or 100 units, and the dispatch is, it has, like, it should produce only 90 units. So it has 10 extra units which he can use it. So this PG minus 10 will give you the 90. So at that time he will try to produce between 0 to 90. Now this PG will be decided by the price as well, whether he wants to charge more or less. If this price is low at that time, he will increase the PC value as well, and this will give the outcome that, okay, what should be the dispatch? The same problem which we discussed earlier, that we are not like stick to the dispatch. We are trying to obtain or performing this self scheduling to identify what should be the dispatch. So we will keep or solve this dispatch in such a way that we are performing some certain charging action. So whatever is the capacity, we have reduced the dispatch uh, like from the capacity, and that dispatch will be reduced to the actual capacity minus charging. That, okay, you can only dispatch this much. Once, if the like we this day ahead price is very high, at that time I want to discharge as well. I want to wind producer will try to make money. In that case, this PC value will become 0, and then PG can have the maximum available capacity. So this PG will have maximum available capacity, and he will ask the storage as well to discharge more. So that is the extra added term in the objective function. Is this clear?
Yes, sir, little bit.
Okay. So this is the one of the objective, or I can frame it other way around as well. Yeah, but it, like, if I frame it like this, instead of this particular term, I can use, okay, let me change the colors. So I can use something else as well, like, lambda DAT PDIT minus PCIT. If I use this term as a object in part of objective function, then I can get rid of this as well. Like, we can remove this one, that my PG should be within the limits. And that part we have discussed in our renewable modeling as well. Like when we discuss the, how a renewable producer should decide by minimizing the imbalance cost. So this PG should be whatever is the P max available. So it will be between that value to avoid any penalties. So that part is driven by the market price, and then he will use, like, we will remove this PC part from here. So putting the PC here dictates that excess energy will go for the charging. If I remove this, then the objective function will look like this, that the PC is coming from the market price and PD is again selling at the market price. So it is, like arbitrator kind of function. But if I put this PC here, it specifically dictates the optimization that, okay, I will only charge whenever there is a excess energy. Okay, so this is the only difference. Otherwise, you can use replace these two terms. So either you remove this one and replace this with this particular term, that is also perfectly fine. Both will give you the similar kind of results. Okay. So once, like, let's say these two type of players are there, you can model for the consumer and prosumer as well. Okay, the consumer prosumer, for the time being, like prosumer have solar in the production, so that can also be used. Now, what will be the objective of storage? Because we have storage here, so storage owner will also have a objective, and it will try to maximize the money he is getting. And how much money he is getting? Like over all time periods, it is basically getting a money for charging rights. So, okay, yeah. selling three type of rights. One is PC, let's say, rights uh, at to the ith player or at a time t, plus PD rights at a time t, plus uh, ED rights at a time t. So we will try to maximize these, and whatever these rights will be basically at the price of PCT, price of discharging at time t, and price of energy rights at a time t. So we will try to maximize this objective function. Now he has provided rights to different players. So what was those rights basically? So we have defined here in a common constraint that this PC max IT is the rights provided to any ith player. Okay, so we have, let's say, different players. So total summation of these players. So let's say summation of I, and over we have considered arbitrator, we have considered wind producer. Let's say similarly is for PV as well. So those kind of players. So we will used some PC max, that okay, these are the rights provided to any player. So this summation should be equals to the whatever total rights provided are supplied by the any storage at any time t. So this will be the total rights provided. Okay, so the total charging rights. So we will sum over individual rights, that okay, these many rights has been supplied to different players, and total summation will be the PCRI. Okay, so this is the total charging rights provided. Now, what should be this charging rights? Can he provide very large value? But no, this charging rights should be restricted as well to
But
the
these rights are in terms of power
yes, so
production.
I'm assuming T equals to 1. So yes, rights are in terms of power, like at a time, this much power you can charge. Okay, if I'm assuming the T is 1, the each time block is 1 hour, then P and E can be replaced basically. Okay,
Yes,
sorry.
yes, sir.
Yeah, if it is you can multiply it with the width of time. Let's say if we are considering the time 15 minutes, then we will multiply with delta T with all these p's, basically that it is only for the 15 minutes. Now it is 1 hour, so that's why I'm using that. Okay, this is the charging power at a particular time t, and then it is going into the energy.
Yeah,
So this
basically
should,
they will take out, mesh the area and find
sorry.
the energy to. Basically, they will find the area under the power curve and
Yes,
match the
yes,
energy.
yes. So let's say this is the capacity of a storage, because each energy storage have certain charging and discharging capacity. Like at a particular time, for a particular time period, they can only charge this much maximum capacity. It's not like you can charge the battery like to the from 0 to full capacity in 1 hour. No, you cannot do that. So that is charging limit basically. Just like the ramp limits of the generators, like they can only boost to certain an amount of power from one time to another time period. Okay, so just like ramp limits of our traditional generators, the batteries can also, it cannot be charged instantly. So this limit has to be placed. Similarly, we can define that over I, I will calculate that how many rights has been provided to the different players, and that will be the total rights provided by the storage S, and it will be this right should be um, less than the overall capacity of the storage. Same goes with the energy as well. The same for energy rights. Okay, So these conditions has to be satisfied, that okay, he cannot sell more than its rated capacity. So whatever rights the storage is provided, it should be bounded by its actual physical limitations, that these are the physical limitations of the storage. uh, is this clear so far?
Yes, sir. Sir,
Okay.
are the voltage levels are different for EV chargers, like in the charging infrastructure?
Yeah, obviously, like with the different voltage levels and the current levels, they are like fast and slow chargers, right?
No, the charging terminals are different. Are they standardized?
I'm not
Basically, I
able
want
to,
bas-
get your question.
basically I want to know, sir, whether the charging terminals that are available for EV, are they standardized to a certain voltage or are they different?
So that depends upon, like generally, they should be standardized because, okay, can I use, okay, let me ask you one thing. Can I
Yes.
use like, my phone's charger, whatever the charger I have, can I use that to charge another phone?
If the terminals are same, means like
Let's say
there are
we
different
have
USB terminals.
like both the chargers are C type.
Yes, sir.
We can charge it.
Uh, Supply is of certain quality, then we can charge it.
Yeah, let's assume the same power point is there, and I'm using one charger from the same power point, and then I use another power point to charge my phone. Like the same power point, but with another charger to charge my phone. Is it okay? We can, I think, charge it, right? Like
Yes,
we
sir.
have different company phone. So it's a phone is also battery. So it's a, what you are asking is this like valid for that example as well. So it's a battery, and at our home we have different like mobile phones, different chargers. Different companies provide different chargers, and we are using them comfortably, I think.
Yes, sir.
Is it advised to use a
No,
different charger?
no.
Why?
Basically, the power quality.
Yes. So there should be standards, and standards are to ensure that uh, universal chargers should be available, and we can use like any charger to charge our particular battery. EVs are the like electric vehicles, and like any battery, they have certain like manufacturing specifications or limitations. If we are using their own chargers, their performance will be high. If you use some other chargers, the performance will be low. That is the only difference, right? If I'm using a fast charger, it will charge very rapidly because the current is high in those fast chargers. If it is slow chargers, the current is low. So it is only about the performance. And if you are talking from the EV point of view, are you talking from the EV point of view, or like from the any storage point of view?
No, sir. Actually, EVs are certain terminals are there where we can charge EV.
Yes.
Like and those terminal output voltage. If the voltage is same, then we can replace the power here with current.
Yeah.
The
So
application
if
can be
the
means where
rated voltage mentioned on those chargers are exactly the same, which is like mentioned by your EV supplier, then you can use them. Obviously, the current will be different. Like if you go to some fast charging station at the point have fast charging, then the current will be different, and it depends. Like you need fast charging because you may be in hurry and you want a quick charge to reach somewhere. So in that case, yes, we will use the fast charging. Otherwise, for batteries it is advised that they should be slowly charged. So if you are not like in a hurry, for electric vehicle point of view, we generally charge it during the night time.
Yes, sir.
right? So it's all about performance of the battery, and standards are there. Obviously, the country to country, the standards are there, and the like the government is coming up with more restrictions on the standards, that okay, if public charging points are there, they should have specific ratings only,
Okay, sir.
right? And we need to tight the standards from the EV manufacturer point of view as well, because sometimes like this Apple charger, we cannot use it. Okay,
Mm.
so if some standards are there, but that is fine, because we can carry our personal charger, so it is not a issue with those particular chargers. But EV, uh, sometimes we cannot carry our own charger. That is the issue, right? And a
Yes,
charger
sir.
means basically we cannot carry the power point with us, and the power ratings are different, then it will affect our performance of the battery. So those issues are there. But most of the time, generally it's a single phase power supply, so we have that rating of 220 to 30 volts, so it will work perfectly fine. And the charger point is basically within our vehicle, so we can connect it, right?
Yes.
Yeah. So if the point is different, then obviously you cannot use that particular public charging facility. But if the point is supported by that public charging facility, voltage voltages are always like standards. We think for single phase supply, it is fixed 220, 220 to 30 volts. That is always fixed. It will never change. Okay.
Mm. Sir, some companies they place public chargers in certain areas. I think
Mm-hmm.
that is DC. Is that DC or AC? I don't know. That's the
Most of the chargers are, I think, like, so
AC
it depends whether the rectification is in your
unit
like
is there.
yeah, charger available in the vehicle. If it is not there, then the power supply will be DC as well. So both kind of things can be provided. I'm not certain about a specific company, like whether the chargers can be AC or DC. So if it is AC, it's simply power supply. It's not charger
Yes.
charging facility.
Yes.
If it is AC, it is simply like power supply, and your charger is basically in your vehicle itself, which is converting that AC into DC. So that is fine. But if it is DC, that charger is already in the point, basically a charging station. That power and current rating, you have to make sure that it is compatible with your vehicle. If it is AC, then it is no issue. AC is
But
standard everywhere.
these equations can also applicable to EV technologies as well, like
Sorry.
renewable producers. The storage owner equation that you mentioned here over here,
Mm-hmm. Mm-hmm.
is that is also applicable to EV
Yeah.
technology?
So basically, what we are assuming is that some network is there. Okay, and renewable producer is also connected here. Our consumers are also connected here. Some PV is also connected here, and some let's say battery storage is also connected here. So this battery storage is on behalf of this renewable, is doing charging and discharging action from the network.
Okay.
So if EV is also connected here, it can also be so vehicle will not use another battery to charge itself, but let's say some, what we call it, charging station. Okay, so some charging station is there. It is acquiring some power from the network. It may have some solar installed. Okay, some solar power as well, and then it is providing the power to our ev ev is charging. So in that case, if let's say enough power is not available in the network, at the let's say prices are very high, in the network, the real-time prices, he can ask storage, another energy storage or large energy storage to supply some power, or maybe store some power for this solar if no load is there or no EVs are present for charging action. Then he can ask the energy storage to do so, provided the round trip efficiency should make the viable solution, right? कि charging discharging में losses भी हो रहा है.
Yes, sir.
So that if it is viable solution, if it is still making some money out of it, then he can do it. Okay. So I will just quickly finish it. So how we can solve this particular problem is, like there are multiple players. They all are looking for different objectives, and they are coupled with this particular constraint. This one. These equations are coupling all of the above formulation, and the same, like the rights for energy as well. Let me put it here. So these constraints are coupling all the objective functions, otherwise they are separate, right? Uh, these three constraints, which are basically defining that how much rights has been provided by the storage. These three constraints are coupling all of these different objectives. So, like otherwise the renewable producer will not affect the outcome of arbitrager. Arbitrager will not affect the outcome of, let's say, if some PV is there. So they will be you can solve them individually, but you can see that this PC max will be restricted, like how much rights he can acquire will be restricted by the physical capacity of the energy storage, that how much, and the total everyone is asking for certain rights, that is the total rights he can provide, and that total right is limited by the physical capacity of the storage, whether it is charging, discharging, and energy. So these three constraints are uh, uh, basically conflicting the objectives of the different players, and basically you can say it is coupling the objectives of the different players. And for this particular problem, we can write down the again the KKD conditions which we have studied earlier for individual uh, player, and then merge all the KKD conditions and we can solve it. That is the basically the Nash equilibrium outcome of the individual players. Like there are multiple players, they are looking for their own objective function, and we can obtain the Nash equilibrium if we solve all of them together, and that will give the equilibrium at the point where everyone is happy. So this is it for today. This session, we will, I think, resume. It's already 1:15, so let's resume 2:15. Okay, because let's have 1 hour of the break, and then we will start the next session at 2:15. So I think, thank you. If you have any doubts, I will answer them. Yeah, thank you.